The next portion in module 3 is single source shortest path algorithm. Single source shortest path algorithm, or the shortest path, basically it is path of the minimum weight. If there is a path from U to V or more, it will be taken as that particular weight, or if there is more than one path from U to V, then the minimum of those paths will be taken. If there is no path, then it will be infinite itself. There are some variants for shortest path algorithm problems. The first variant is single source shortest path problem. From the name itself, it's written, or you can understand, there is only one source. Find the shortest path from S to each vertex V, where S is the single source and V are the vertices. The next variant is single destination shortest path problem. Now there is only one destination. From other vertices you have to find out what is the shortest path. Find the shortest path to a given destination vertex T from each vertex V. Next variant is single pair shortest path problem. For a shortest path, or find the shortest path for from U to V for a given vertex U and V. And the last one is all pairs shortest path problem. Find the shortest path from U to V for every pair of vertices U and V. So what's the difference between the third one and fourth one? In the third one, there is only one pair given. In the fourth one, all the pairs, all the shortest path between all the pairs has to be calculated. The negative values can be formed without cycled graph. We had already studied about that Bellman-Ford algorithm. The same procedure is going to happen in the next also. Shortest path. In all the shortest path algorithms, there is a step known as a relaxation. Now, what the relaxation means is that if a particular value at one particular vertex is less than the value added to it, then that will be taken, or else you have to add the new value. That means relax u comma v. That means there is an edge between u and v, and you have to find out, or you have to perform this relaxation. If the cost at v, already present cost at v, is greater than cost at u plus w u comma v, weight of traveling from U to V, then you have to add this number. That is, we are going to find out the shortest one. So you have to put the smallest value. So D of V should be replaced by that added number. And you have to know from which, there may be multiple paths, so you have to know from which source you had taken, or for which vertex you had considered this. Now let us do this using an example. Now this is an example where there are 6 nodes RSTXYZ. Now here S is always taken as a source. So that is why the value at S is put as 0 and all others are infinity. There are some negative as well as some positive. There are no cycles, so this can work out. Now S has, when starting the traversing, S has two outputs or two outgoing signals, one to X and one to T. Now let us find out what happens next. It has taken that value. At each node that relaxation happens. Now for the first case, relaxation between S and T happens. The value at T was infinity initially. If you add 0 plus 2, that is d of u plus v w of u comma v, if you do that you get a value 2, which is much lesser than the infinity value, so that has been replaced. This is very evident from this. You have done all this earlier. So similarly this goes on. At t it is 2, at x the infinity was changed to 6. Now considering t has two outgoing, one to y and one to z. So y was replaced by 6 and z was replaced by 4. Next you need to consider x. X has two outgoing, one to z and one to y. Z has already been considered, but still you have to consider it once again. 6 plus 1, it used to give 7 to z, but you have a much lesser value, so no change. 6 minus 1 is 5 to y. Next one you have to take from y. Y is 5 and it has one outgoing edge to z. Z had a value 4, but y, the value at y minus 2 is giving a lesser value, so that 4 is replaced by 3. Now, by 3. Now, all the nodes have been visited except for R, because R doesn't have any incoming into it, so it will be infinity as it is. So that's the end of that example. Coming to the generalized shortest single source shortest path in DAG, you know what a DAG is, directed acyclic graph. In that, the algorithm goes this way. The input to this algorithm is a graph and the source vertex. It is done, topological sort is done on each and every vertex. Now the topological sort we have already discussed earlier. So initiate G comma S for each vertex U taken in the topological sorted order. You will have to consider the adjacent list, and from the adjacent list you have to do the adjacent list gives you the connected edges from each vertex. Relaxation has to be done and you get the answer. Now coming to the time complexity of this algorithm, it runs in a linear time of b plus e. For topological sort it was b plus e. For initialization it takes b plus e. For loop it is b plus e. That is, you have to go through all the vertices as well as you have to consider all the edges. Whether you take it or not, it's another case, but you have to calculate it for all the vertices as well as from all the edges. You cannot keep it aside. So the time complexity for single source shortest path in DAGs is big O of v plus e, where v is the set of vertices and e is the set of edges. Thank you. Now considering about the negative weights, usually the shortest path has to be considered, or shortest path has to be calculated for non-negative weights. No problem as long as no negative weight cycles are reachable from the source. Otherwise it is put as infinity, minus infinity. Usually there shouldn't be a cycle either. Only then the shortest path works, or it goes inside a loop itself. You can consider if in this figure, the first figure, there is a path from S to G. There are many paths. If it takes the second path, what will happen? It goes from S to C, C to D, D to C, again C to D. That keeps looping. It doesn't come out of that. It's a negative as well as a positive. So naturally, it goes on looping. In the second one also, it goes on looping. It doesn't stop anywhere. So there shouldn't be a cycle, or there shouldn't be a negative cycle, as well as this works usually well with non-cyclic ones.